Welcome to our presentation of our CS590 Parallel Computing Final Project, Professor Alvin Liebeck. We did this in collaboration with Professor Alberto Bartesaghi at Duke and Alejandro Silva, and we really appreciate their help. What we are implementing is rotationally invariant BM4D with CUDA Acceleration, and let's break that down. To begin with, let's consider this. We have some data in 3D that we took from very small microscopes. And obviously those measurements that we got are going to be very noisy. And our question is, can we recover the true molecular structure, let's say, of using just those noisy 3D data? Our data looks like this. What we are trying to do is we take a 3D volume that we're representing as 2D on the left side, and that's very noisy. And we wanted to see, can we transform and denoise it to get an estimate that looks like the one on the right? So to do that, there's an algorithm called BM4D, which is block matching and four-dimensional filtering. So intuitively, it makes a lot of sense, and let's break it down. To begin with, we take the entire 3D volume, and within that 3D volume, there are many smaller reference cubes that we can choose. For each of these reference cubes, we want to see if that structure exists in that cube, isn't it likely that it will exist in some way or form in another part of the volume? And the answer is yes, of course, that usually is the case. So we take that reference and we try to see, does any other patch or small cube look like that reference cube? If so, we gather it into a stack, a 4D array, hence the 4 in BM4D. Next, we perform some filtering, which in essence takes that 4D stack and says, we have the same structure in all of these. We want to see, can we denoise it using all of this redundancy to figure out the true denoised structure in that image or in that volume. Now, there's one small problem with the regular standard BM4D as it's implemented. If we have the image on the left and we have the image on the right, the algorithm would tell us that they are not similar, because if we compare the values, they don't match exactly because one is rotated to the other. We have a solution to that. That is called rotationally invariant block matching, RIBM. Rotational invariant block matching will compute the optimal rotation to get that volume on the right to look like this, the one on the left. So then we say, hey, these do look similar. Now, as you can see, we have more data in that 4D stack to choose from and more redundancy so that we can get an even better denoised image as a result. So here's what the overall process looks like. We have on the top left our 3D volume, and within that we have the smaller reference patches, just like in BM4D. Then what we do is we apply a mask. So we basically consider the sphere within that cube. Then we want to know throughout that entire 3D volume on the top left, is there any other patches that look similar to it even after rotation like we were seeing? That's the RIBM part. Then we take that 4D stack of match patches and then we perform 4D filtering and aggregation to get one single estimate of the denoised patch. And then with that denoised estimate, we update the original volume in place of where that reference patch came from. Now, something you might notice is this is going to take a lot of computational power. And in fact, Professor Bartesaghi and Alejandro Silva have implemented a similar algorithm, which is rotationally invariant non-local means, which also does denoising. And that takes days for a large CPU cluster to run. So we want to know, is there any way we can make that even faster? To do that, we use what we've learned in this class, which is of course parallelism. And to do this, we just take a look at our data here. We have a 3D volume and we're taking one reference patch and trying to gather everything up, filter it, and then get one denoised patch to put it back in. So we have a lot of those, right? Can't we do that in parallel to speed things up? And the answer is yes, of course. Each of those is independent, each reference patch is independent from the others, so we can run the same process on all of those reference patches at the same time, which will give us a huge performance boost. And a perk of this is that if we consider having to do parallelism for each of those small implementation details, that is going to take a lot of work to implement. Instead, by implementing it on this higher level for each reference patch, we're doing those in parallel, we can save a lot of work from implementing each small detail in parallel and rather focus on doing one thing at a time sequentially, in other words, for each reference patch. So let's break down the first part of that process of RIBM, which is, of course, trying to calculate similarities between a reference patch and a potential block match. So to do that, we have three main steps. The first step is basically a processing stage. We apply a Gaussian mask, perform a 3D discrete FFT and FFT shift, and then we convert to spherical coordinates. Using those spherical coordinates, we pass it into a library of kernel functions called QSoft, which we have implemented from a implementation we found called soft. And of course, we had to change those implementations to use CUDA acceleration, and that's why we call it QSoft. QSoft finds optimal rotation values to match B to A. In other words, we have a potential block match B, and we want to see, can we rotate it in a way that it looks similar to A? And if so, we take that B, rotate it to look as close as possible to A, and if they're similar enough, we add it to the stack to do denoising for the reference patch A. Let's break down each of these and look at the implementation details and the problems we face along the way. First of all, after we apply the Gaussian mask, we have to perform a 3D discrete FFT and FFT shift, and then convert to spherical coordinates. Now, while there is a library implemented in CUDA called QFFT, this was not able to satisfy our needs for the project because what that does is it does parallelization of the FFT. But what we had, remember, is parallelization of the reference patches. So we're sending a lot of reference patches at the same time. And so instead, we want to be able to call kernel functions from that kernel to perform FFT for one of those at a time, and without having to worry about those conflicting with each other. So to do that, we use something called the SOCM algorithm to perform the FFT. And there's more details in our paper if you'd like to read about that. Then we perform the FFT shift. And finally, we had to do something called spherical harmonic representation of the data to integrate basically the Fourier transform volume along each angle to calculate the spherical representation. And this uses something called trilinear interpolation, which we will talk about really soon. Next part is QSoft. And this was pretty hard because we had to take all of the soft functions that were implemented in C and convert them into C++ so that they would use CUDA. And so we actually had to implement the kernel functions in CUDA. And what was even harder than making these functions was actually managing the memory for all of these functions. Next, we had to perform the rotation. And rotating these 4x4x4 patches, which is what the size that we chose, is kind of tough because if you rotate it, you're going to have values in between that you need to interpolate. So that's where texture memory from NVIDIA's GPUs helped us. Texture memory can do trilinear interpolation of 3D volumetric data very quickly. In fact, if you ever play games on your PC, the texture memory of an NVIDIA GPU plays a really important role in rendering the game world quickly. Without getting too much into detail, the architecture passes information from the texture L1 caches to filters, which are engineered to perform trilinear interpolation really quickly. This saved us a lot of time in one of the most computationally intensive steps of the algorithm. Speaking of computationally expensive, let's talk about what we actually were hoping to achieve from this setup. So first of all, we want to know First, does this even work? To do that, we wanted to measure the performance using PSNR on the data we showed earlier. So what we took is we took that original volume and then added synthetic noise to it so that we could try to see how our algorithm performed. So with different noise levels, we tried to see, will it outperform the actual BM4D that has already been implemented? And will that rotationally invariant block matching step actually add to any performance gains for us? So as it turns out, doing even this type of volume was very, very computationally expensive. So we focused on a smaller patch, 50 by 50 by 50 volume that we took from the exact same data, and then we cropped it to get this. Now from this data, we wanted to see two things. First of all, does it denoise well? Does it do better than the BM4D based on the PSNR in gains? Second of all, we want to see, does it speed up compared to implementation on the CPU that we talked about, rotationally invariant non-local means given by Professor Bartasaghi and Alejandro Silva. What we are hoping for is at least a 10 times speed up. First of all, let's go back to performance evaluation. From this chart, it is very obvious with RIBM4D, our implementation in red, performing much, much better at higher noise levels, where the PSNR change, basically how good the algorithm did at denoising the data performed, the higher the better. We saw big gains at 0.2, 0.25, and everything above that did much better than the standard BM4D. It is interesting though to see that the algorithms, both the BM4D and the RIBM4D, did not perform that well with a lower noise level. That could potentially be because the algorithm is just not suited to volumes with very low noise. Next, let's talk about runtime evaluation. On the y-axis, we have the number of seconds, and we actually ran our algorithm on 3 different GPUs, the fastest being Tesla V100. For us, it took 340 seconds to run the algorithm on the 50 by 50 by 50. Now, let me tell you why this is absolutely amazing. Remember how I said that the rotationally invariant non-local means, which was the denoising performed by Professor Bartasaghi and Alejandro Silva, took multiple days to run? That took 120 hours on 1,659 CPUs. With our estimates, we would be able to perform the same thing, which is rotationally invariant BM4D, which is a more computationally expensive algorithm than the non-local means that they implemented. And that only would take 28 hours on the same data with just one GPU versus the CPU cluster, which uses 1659 CPUs. That is a huge performance increase, and we are really happy to see that. Now let's talk about what we can improve on in the future to get even better performance, both in the denoising and in the actual runtime itself. To begin with, we can optimize cache structures, and that would be able to potentially make a big impact on the performance of our algorithm based on runtime. Next, we would be able to exploit symmetries. And this is, let's say we know something about the data. We know that it's symmetric along a certain axis. Then we're able to do better denoising since we have more information about it. Third of all, we can do multi-GPU computation. In other words, let's take multiple GPUs and run them at the same time, and we would think that we get even more speed up from using that multi-GPU setup, potentially making that runtime much, much shorter than the CPU cluster. If you want to take a look at our code or our report, it's all at the link of our GitHub for this project, and you can check that out over here. Again, thank you so much for watching. Thank you so much to our Professor Alvin Liebeck for this amazing course where we learned a lot. And thank you so much to Professor Bartasaghi and Alejandro Silva for their mentorship and help throughout this project. Thank you.